Ladies, gentlemen, the otherwise fabulous, welcome. As stated, we're going to be talking about a packet's journey through PF. So yes, yet another firewall. We're FreeBSD, we get that a lot, the yes, another firewall. Very briefly, who am I? I'm Christoph. You can get me on kp@freebsd.org. I've been maintaining PF in FreeBSD since 2015, and yes, I do feel old when I say this. Started out 10 years ago looking at PF. It doesn't really handle IPv6 fragments particularly well. I bet I could fix that. Those of you who have experience with open source projects are groaning right now because you can never ever escape this again. So as I said, I've been doing that since 2015, since 2021, and that's why I brought the hat. I've been contracting for Netgate, and I've been maintaining PF in pfSense since then, so thank you very much, Netgate, because I do like food. Very briefly, this talk is based on FreeBSD main as of about today. There's been a little bit of refactoring work that has been stolen, imported from OpenBSD. They still have theirs, it's fine. This talk is also inspired by, there we go, I've avoided the S word, by a talk called A Packet's Journey Through the OpenBSD Network Stack by Alexander Bloom. It's quite a good talk. It's on YouTube. It was presented at EuroBSD in Dublin in September. Here are the slides. I would recommend it, especially because this talk is sort of a spiritual successor. Alexander talked about the network stack at large. I'm going to talk about the firewall, but you kind of have to... Yeah, but I don't want to be on the camera. Anyway. Nobody wants to see that. So Alexander talked about the network stack at large. You kind of have to understand how the network stack works to understand how the firewall fits into it. Unfortunately, I ran into trouble compressing a 50-minute talk into an introduction to a 25-minute talk. So there we go. These are the essence. Everybody's seen this. Everybody's understood this. Moving on. The main things to keep in mind here is this is a very simplified version of how stuff works. But essentially, packets arrive on the hardware. The device driver does things to speak to the hardware, delivers Ethernet packets into the Ethernet Ether input function. Yes, I have assumed that all networking is Ethernet. It's okay, everybody does it. It's because all networking is Ethernet. The Ethernet function will demultiplex this. We'll go look at the packet and decide, what type of packet is this? Is this an ARP packet? Is it an IPv6 packet? Is it an IPv4 packet? This is a legacy presentation, so this is IPv4. It really should have been IPv6. Your Ethernet input function goes into your IP input function, which, depending on where the packet is intended to go to, might cause forwarding to happen, so pass the packet on to the next router, or it might be an input packet, again with demultiplexing based on your IP protocol field. Is this a TCP packet? Is it UDP? Is it ICMP? Is it God knows what else? And then we might hand it to the socket layer for local processing. Same thing on the output side. If you have a TCP socket, you will TCP output, you will IP output, Ethernet output, hand it off to the device, which will throw it on the network. And if you're very, very lucky, your packet will actually turn up somewhere else. Main things to remember when you're hacking on network stacks is the order of operations here is different. When packets come in, you do Ethernet first and then IP and then TCP. When packets go out, you do TCP first, then IP, then Ethernet. Or possibly you do, Ethernet, IP, Ethernet when you're forwarding. So where does the firewall fit into this? Right there. So in FreeBSD we have your choice of firewalls. You can have PF, that's the one I work on. You can have IPFW, that's the one done by smart people. And then there's also IPF. So because we've got these multiple firewalls, we just don't have code in the kernel that goes if PF, then call PF input, if IPFW, do IPFW check or whatever. We've got an abstraction layer called netpfill or pfill, and that hooks in at appropriate locations. So I've only really illustrated input and output on the IP layer here. There are also hooks where you can do layer 3 filtering. There's even some very strange things that Netflix do where they actually hook into the device driver, even lower. There are layer 2 hooks here. I've not shown them here because PF does do Ethernet filtering, but we're not going to talk about that here. Key concepts for PF is that it is a stateful firewall, so states are important. You need to remember that those exist. And we are a stateful firewall even for stateless protocols. So I'm sure we all know that UDP is a stateless protocol. You send the UDP packet, and as far as the protocol is concerned, there is no other packets. It's just a UDP packet. In practice, however, you like to do things like get a reply. So what do we use UDP for? Basically only DNS, right? And when you send a DNS query, it is a UDP packet that goes out to port 53 from whatever source port you've selected. But to be really useful, you kind of want to get an answer to that packet. So there is a reply packet that is source port 53, destination port, whatever source port you picked. And then PF will recognize that, actually this UDP packet belongs to a state that I've created for this UDP packet. So you can configure your firewall and say, I will allow outbound connections to port 53, and you don't need to worry about the reply. That is implicitly going to be allowed as part of that state. The next concept, of course, is rules. Your firewall is not particularly useful if you can't tell it what you want it to do. So I like to describe firewalls as policy instruments, where you can decide that, this is the type of traffic I want to allow, traffic to these addresses, to these ports, these protocols, whatever you want it to be. And that's defined in rules. So rules will end up creating states. What happens when we hit the pfill inputs? These are the main functions that you need to understand. We hit pf test. Actually, that's a lie. We hit pf check in or pf check 6 in or pf check out. But those functions don't do much. They all just call pf test. So you end up in pf test. First thing the pf test function does, and it does this for every single packet that pf deals with, is it calls the pf setup pdesk, which parses the packet. It sets up a pdesk or a packet descriptor with a whole bunch of information about the packet. So a lot of stuff like what's the source IP address, what's the destination IP address, what interface did it come in on, what's the protocol, what's the source port, what's the destination port. All of those things get set up in a separate descriptor, so we don't have to parse and reparse the packets. We do that once. What it also does is what PF calls packet normalization. And the most important thing it does in the normalization step is reassembly. Because packet fragmentation is a thing, yes, even in IPv6, which is part of the reason that I have this much gray hair is IPv6 packet fragmentation. But we have to reassemble the packet, because if we don't see the full packet, it is entirely possible that we don't see the headers. So if we want to make a firewall decision on a packet, quite typically we care about the layer 4 protocol, TCP, UDP, SCTP, ICMP, and we want to say we want to allow TCP to port 443, for instance. We really need the TCP header to be able to make that decision. So we reassemble the packet and we look at the fully reassembled packet until we're all the way done with it. There's a special case for v6 which hopefully we'll get to. Typically we only really look at layer 3, the IPv6 header, and layer 4, the TCP UDP. If it does not find a state, this is a packet that is creating a new connection. So ideally it's TCP SYN or it's the first UDP packet you've seen. Then we will evaluate the rules, which is pf test rule. We'll iterate through all of the rules that we have configured, see if they match the packet, and eventually get to a point where we make a decision. Either way, eventually there's output handling, and there's only so many things that you can do to a packet, right? You can pass the packet, you can say, yes, I approve of this packet, you can continue on your way unmolested. We can drop the packet, which is when we don't approve of the packet's sense of style or whatever, why ever we decided that it's not a good packet. We drop it on the floor and bye, it's gone. We can route to, which is PF's policy routing, where you can say that, yeah, okay, my default route says that the packets need to go that way, but actually if it's this specific port and this specific protocol, I would like you to send it that way instead. We also have AF2. This is new. Well, it's new in FreeBSD. It's address family translation. It's NAT64. It's doing unspeakable things so that your IPv6 clients can talk to the IPv4 internet. This is very new. This is work sponsored by Netgate. And it's going to be in FreeBSD 15 and the upcoming pfSense 2503. And then IPv6 is special for your output handling because we may have to refragment. So we're familiar with fragmentation, right? We have a large packet, we want to send 20,000 bytes of data. Unfortunately, Ethernet is terrible and you can only send 1,500 bytes of data in one go. So you chop the data up into fragments, you shove all of the fragments through the network all individually, and then eventually you put them all back together. As we've discussed, your firewall has to put them back together as well. And for IPv4, this is simple. You've put the packet back together, and then we just hand it to the output codes, to IP output. And if the 20,000 bytes don't fit down that link, it'll just refragment it for us, and everything will be okay. IPv6's fragmentation is different. So those of you who were taught IPv6 might have been taught that there is no fragmentation in IPv6. That's not quite true. There is no intermediate router fragmentation in IPv6. So in IPv4, every single hop can chop your packets up into smaller pieces. In IPv6, they are not allowed to do this. If you get to a point where your packet cannot fit down the link, you don't fragment it. You send an error message back to the sender with, yeah, I'm sorry, but you sent me 1,500 bytes and I can only fit 1,400 bytes down this link. And then the sender will split his packet up into 1,400 byte chunks and send them on. And then potentially discover that the next router says, yeah, I can only fit 1,300 bytes down this, and then an error message goes back and you try again with an even smaller one. This is called path MTU discovery. If people don't block ICMP, this actually sometimes even works. But we can't break this in our firewall, so we've got this reassembled IPv6 packet that's 20,000 bytes, and we can't shove it down a 1,500 byte interface. So we have to refragment the packet, but we have to remember what size of fragments we got when they came in. And then we refragment along the same size. Actually, for simplification, what we do is we look at what is the largest fragment that we've seen, and we refragment based on that size. Now, typically, your implementation is not going to be stupid, and that is just going to match exactly the same packet sizes that came in. But it means that because we respect this packet size, your path MTU discovery is going to keep working, which is kind of important. Even though fragmentation is not typically a thing, all of the internet is TCP, right? And in TCP, you make sure that a single single TCP packet passes in whatever you want to do. It's a stream, and TCP takes care of all of the reassembly. Now, there are some implications to this design. You may remember that the first thing we did for a packet in pftest state protocol is we look up a state. Now, this implies that it doesn't matter what your rule set is. If there is an existing state for a connection, it will pass. So as a PF user, you should be aware of this, that when you change the rules, even if your new rule set would mean that a specific connection is not allowed, if the connection was established before you set your rules, the connection will continue. Sometimes you want this, sometimes you don't. If you don't want this, you can flush existing states, you can kill specific states, but be aware that this is a thing. As I said, block all might not actually block everything. What it also implies is that this state lookup is quite important because we do this for every packet. How does this work? We keep a hash table of states. So we have a very big hash table, and we hash states based on their source and destination IP address, source and destination port, address family, so that we don't mistake IPv4 and IPv6 connections for each other. and then whatever protocol it is. Based on these things, we can find a specific hash row, and then every hash row has a little linked list that we can iterate through and go, are you my state, are you my state, oh, you're my state, and now we can continue. You can configure how big this hash table is. There's a sysctl, or a tunable rather, net.pf.states_hash size. This is important because if you have many more states than you have rows in your hash table, you will end up with many states in every single row, and there are many hops on the linked list that you need to walk through before you find your packet. As a general guideline, try to have as many rows in your state hash table as you expect to have states. So if you're dimensioning your firewall for 10,000 states, or 100,000, or 1,000,000, you want 10,000, 100,000, 1,000,000 rows. You can be off, by a factor of 2 in either direction, and it'll mostly be fine. But if you're off by more than that, it's going to hurt. If you have too many rows, you've wasted memory. Memory is cheap. Probably almost always better off wasting memory rather than not having enough rows, but it is something to keep in mind. There's actually a DTrace probe that is quite interesting. So DTrace lets you do dynamic probing. You can know when certain events happen in the kernel in the middle of a function. We have some static probe points that are defined in the code that when you get here, these are the values that you can measure. And one of them runs in the purge thread, so that's a background maintenance task in PF where it will clean up old states and potentially old rules. And so it runs through this entire state table every so often. And for every row that it runs through, it can tell you, I'm in row number 45, and actually I had 3 states in this row, and I'm in row number 46, and I have 1 state, and I'm in 47, and I have 0 states. So you can build a histogram, you can monitor how your utilization is there. Another thing to remember that is potentially interesting to know is, due to the way state limits are implemented, actually hitting your state limit is quite expensive. So you don't want to be in a situation where you're constantly pushing up against that limit. What else is important? We have a control plane, which is how you interact with PF, either through a utility, pfctl, which you may all be familiar with, or programmatically. For the kernel, it's all the same thing. There's an API towards the kernel, and right now, in PF, there are 3 different ways to do this. This is because of historical reasons. It started out with an ioctl interface, basically where you copy structures in and out of the kernel. This is simple, this is relatively efficient, and this is a pain in the everywhere when you want to make changes. Because you modify the struct and all of your fields move around, and user space and kernel have a different idea of what the struct layout is, and nothing works. So it becomes very difficult to make extensions, to teach PF new tricks, which we've been doing. So one of the ways to deal with this is actually what they did in what they described in the previous talk for NPF is NV lists, name value pairs. You have an abstract representation of what you're sending backwards and forwards, into the kernel, out of the kernel. And that means that when you add fields and one side or the other doesn't know about this field, it just ignores it and everything works. So this is good, but there are performance implications. As discussed in the previous talk, the experience in FreeBSD was it worked fine right up until we tried to use it for state export. So you can get PF to give you a list of all of the states it knows about. And if you have 100, this is fine. If you have 100,000 or 1,000,000, this is very much not fine. Not fine to the extent that I think we topped out at maybe 2 million states. And then we were copying 4 gigabytes of data between the kernel and user space. Yeah, that was painful. Painfully slow as well. So the new shininess is Netlink. Yes, that Linux thing. I like to describe it as solving more of the problem than what ioctl plus nvlist does. It also has this notion of type length value encoding for your fields, so you can add new field types without confusing the other end of the connection, even if they don't know about it. But the really nice thing is its efficiency. It's essentially just as fast as the old ioctl style, but because it can stream data out, when you're exporting 2 million states, you get a peak memory use of 16 megabytes, trivial amounts of memory actually in use. So it is both fast and memory efficient, and it gives us the flexibility of extending interactions, which again is really important if you want to have new features, because if you want to teach PF to do things like address translation, address family translation, NAT64 things, you need a way to configure this. You need additional fields in your rule structure, so you need to be able to make those changes. My hope is to migrate to Netlink for everything and then just get rid of the old interface. I point this out because if you are writing an application to interact with PF, there are multiple ways that you can do this, right? You can just exec pfctl and pass information into it standard in or standard out, which sometimes is the right thing to do, but I abhor the notion of forking off other binaries to do work for you. It's just ugly and error handling is terrible. But sometimes it's the right thing to do. What you want to do is, there is a library called libpfctl that makes abstraction of these things, so it just gives you some functions and some structures that you can fill out and interact with or get information out of PF that way. It's actually what PF uses. It is also a work in progress, so not everything is implemented this way, but every time I make changes or I convert stuff to Netlink, they get a libpfctl function for this. So if you're going to build a new tool to interact with PF, please, please, please look at this, or just exec pfctl. Do not try to interact with the ioctl interface yourself, because sooner or later I'm going to break it for you. You've been warned. We're in FreeBSD. We try to be very good about backwards compatibility and things like that. But I'm not going to keep maintaining the old ioctl code once it's no longer relevant for mainline PF. It is going to go away at some point. I think we have some time for questions, if you would like. Otherwise, I have some spare slides and I can talk about some other things. Was everything completely clear? Yes? So the question is, how close is FreeBSD PF to OpenBSD PF and NetBSD PF? So I am not at all familiar with NetBSD PF. My understanding is that it is essentially unmaintained there. But bear in mind that I am not very familiar, so I might be completely wrong. But I do see the NetBSD people nodding. I saw some noise in NetBSD that they would like to kick it out at some point, but that has not happened, right?
Will happen soon.
Okay, so PF in NetBSD is going to go away soon, so I can stop talking about that one. OpenBSD PF is the source of FreeBSD PF. That's where it came from, so they share a history. The implementation is different. FreeBSD PF has a couple of features that OpenBSD PF doesn't have, and vice versa, definitely. The main things that PF gained in FreeBSD are performance changes. So OpenBSD still have, they are in the process of removing it, but they still have essentially one big kernel lock or one big network stack lock. So you get into PF, there is one lock, and there's only one core that can work on PF at a time. FreeBSD PF, and this is not work I did, this is work that Gleb Smirnov did, I believe, years ago, to make PF be able to use multiple cores at the same time. And essentially the way this works is you have a read-write lock on the rules. So every time you come into PF and you need to do something with the rules, you take a read lock and you can have as many cores as you like with that read lock at a time. And then when they need to manipulate states, they will lock the hash row of that state. So as long as there's no other states in that row, or not too many other states in that row, other cores can be operating on other states at the same time. So that's the locking. So you do get a fairly substantial performance difference there. One of the other differences is 5 minutes. Thank you. Is VNet support. It's the virtual IP stack thing for jails that we have in FreeBSD. PF is aware of this, so you can have a PF per jail, which is a really, really, really useful feature to have, both because it gives you flexibility in your jails, but also because I use it for testing. So I can spin up 2 jails, set a PF rule set in one of them, throw packets from one jail at the other jail, and see what happens. So we have a whole bunch of automated tests in FreeBSD for PF, thanks to that feature. I also recently added SCTP support to PF. That's also only in FreeBSD PF. Other than that, there's a whole bunch of refactoring work that is in OpenBSD PF that is not in FreeBSD PF, although a lot of it has been moved over already. So when I said that there is only one PF, so there's, you enter PF, you get into PF test. Used to be PF test and PF test 6. Those have now been unified in FreeBSD main, and that's something that was imported from OpenBSD. So I'm in the process of importing patches from OpenBSD, minor bug fixes, small new features, but there's still a lot of stuff in OpenBSD that's not in FreeBSD yet. Some of it might never get into FreeBSD. The OpenBSD people take a little bit more of a liberal attitude towards backwards compatibility, so they will just change the syntax and then it'll break. Your existing rule set will break. And there are good arguments for doing things that way, but there are also good arguments for backwards compatibility, and that's kind of a philosophical difference there. Next question.
Can you comment on the difference between FreeBSD PF and NetBSD NPF? Because both are kind of, as you said, working on making the multi-core story better.
Yeah. So can I comment on the difference, the design difference between PF and NetBSD NPF? Unfortunately, not really. I'm not very familiar with the NPF internals. So I can't really tell you, I can't say anything meaningful about the NPF design. I just don't know what it is. So question is, if I want to build a powerful PF-based firewall, what do I invest in? So now, because my customer is here, my obvious answer is you should just give them money. But what you care about, well, in part you want the fast network cards. We can talk about 1 gigabit network cards. It doesn't matter what firewall you use; they'll all do it just fine. So you want the 10, 40, 100 gig network cards. You'll want multiple cores, because PF is actually able to make use of that to some extent. There is still contention internal to it, but it can do this. You want some memory, but really it's not that insanely much memory. If you're buying, 32, 64 gigs of memory, it's almost certainly going to be plenty. I don't know the numbers off the top of my head, but you can go a long way with 32 gigs of memory. So beyond that, fast individual cores, but a sizable number of cores. Last time I ran performance numbers, I think PF topped out on my hardware in my specific setup something on the order of 18 million packets per second. Thank you all very much for your attention and your time, but I'm going to be kicked out now. I'm going to be down at the FreeBSD stand in K, so if you have further questions, feel free to find me there.